For this video, we will be analyzing Norton equivalent circuits. Now, the importance of this is three simple reasons. Norton equivalent circuits simplify the complex circuits into a single current source and parallel resistance. It focuses on the effect of the network on a single load and makes recalculations easy for when changing loads and applying to various circuit types. For this problem, we are asked to calculate the Norton equivalent current. Now, upon inspection, I see that we have our resistive load, and applying Norton's theorem, we will replace this load resistance with a shorted current we will denote I in O. And in order to solve this, we will need to identify our node voltage at the center. It is important to understand that during a Norton equivalent analysis, our terminal A voltage is equal to our terminal V voltage. So, knowing this, let's solve for our V1. Well, adding up the currents of all three branches flowing in and out of the node, we see that our first branch will have a voltage potential of 20 volts less our node voltage divided by the resistance of the branch of 4 kiloohms plus the voltage of the second branch, which also 20 volts less our node voltage divided by the total branch resistance. And these two will be equal to our node voltage, V1, divided by the resistance of the final branch, 2 kiloohms. It is important to note that this actually is less 0 volts, since this is a ground on the other side of this element. Simplifying and solving, we are able to conclude that our V1 voltage is equal to 10 volts. Moving forward with the problem, in order to solve for our equivalent current, we need to identify the total flowing currents of our node at terminal B, as these two will be equal to our I naught. So, solving this, our I in O is going to be equal of the branch current here, which we've already evaluated, will be 20 volts less our V1 divided by 4 kiloohms plus our branch current of the second, which will be 20 volts divided by 4 kiloohms. Plugging in our variables and solving, we were able to conclude that our I in O is equal to 7.5 milliamps. And that is our Norton equivalent current for this problem. For this problem, we were asked to calculate the Norton equivalent resistance. We can start by omitting the resistive load element, and then we will need to transform our voltage source. We can remove the voltage potential of this device by replacing it with a wire. Now, the resulting circuit can be represented as the Norton equivalent resistive circuit, R in O. And solving accordingly, the equivalent total resistance of this circuit is 4 kiloohms, which is in parallel with the following elements of 4 kiloohms, which is also in parallel with our 2 kiloohm plus our final 4 kiloohm element. Now, solving accordingly, we can write the equation as follows. 1 over 4 kiloohms plus 1 over 2 kiloohms, and the reciprocal of that summation, plus 4 kiloohms plus 1 over 4 kiloohms all over 1. Solving and simplifying, we are able to conclude that our RNO is equal to 1.818 kiloohms. For this problem, we are asked to calculate the Norton equivalent current and the Norton equivalent resistance. Now, let's signify our current flowing between terminals A and B as our I and O. We will also need to remove our resistive load element and replace it with a bare wire. Now, solving accordingly, our I and O will be equal to, well, this is a current divider problem, so we're going to need to have the resistance of the opposite branch we are evaluating divided by the total resistance of the circuit, which will be 24 ohms plus 8 ohms, multiplied by the current flowing through the opposite branch, 16. Solving and simplifying, we have our term here is equal to 1 over 4 multiplied by 16 gives us a I and O of 4 amps. Next, we will want to identify the Norton equivalent resistance. This can be evaluated by removing the load completely with an open circuit as well as transforming all sources. Now, we have a constant current source of 16 amps. We will need to transform this by omitting the current flowing through this branch. This can be do so by inserting an open circuit. The resulting circuit will have an equivalent resistance R and O. Solving accordingly, R and O is equal to 24 flowing through our series branch. We have an additional 8 ohms before returning back to the terminal. This is equal to 32 ohms. Finally, we can write our equivalent circuit as follows. And this will be in parallel with a constant current source. Our current flowing through our source will be 4 amps, and the equivalent resistance will be 32 ohms. This here is our Norton equivalent circuit.